Imagine gaining an unparalleled understanding of orthopedic implants that sets you apart in the medical field. This video isn't just about what implants are, but why they behave under stress, integrate biologically, and sometimes fail. If you want to elevate your comprehension of implants and not just memorize names, stay with me. We're diving deep. Welcome to Ortho Implants for Life, where we dissect implant science, materials, biomechanics, and failure mechanisms, so you don't just know what but why. Disclaimer: this content is for educational purposes. Always consult up-to-date clinical guidelines, implant manufacturers, and peer-reviewed literature before making decisions in practice. Beyond the surface, next-gen materials, porous tantalum and biointegrative alloys. Porous tantalum has emerged as a benchmark biomaterial. It combines high porosity, excellent corrosion resistance, strong osseointegration, and a lower elastic modulus relative to some metals. The porous interconnected pore structure allows bone ingrowth, reduces stress shielding, and improves primary stability. Also T6Al7NB as an advanced titanium-niobium alloy, known for better biocompatibility and corrosion resistance compared to the older T6Al4V in certain applications. Smart polymers and drug-eluting coatings. Biodegradable polymers such as PLA, PGA, their copolymers, are being explored, mixed with bioactive ceramics or with coatings that elute antibiotics and growth factors. These enable localized therapy, better healing, and potentially reduce implant removal or infection risks. Also, bioactive coatings on metals, e.g. tantalum, cobalt, titanium, modified to improve hydrophilicity, antimicrobial action, and osteoblast responses. For example, surface modifications of porous tantalum improve immune regulation, bacterial inhibition, and osteogenic differentiation. Ceramic composites. The newer ceramic composite materials such as bioactive glass, calcium phosphate composites reinforced with ceramics offer high-strength, good wear resistance, and excellent biocompatibility. These are increasingly used in challenging joint replacements, especially where wear or corrosion of metallic implants is a concern. The blueprint of success: precision design and engineering. Finite element analysis (FEA) as a predictive tool. FEA is now regularly used preclinically to model stress distribution, micromotion, and risk of aseptic loosening. A 2024 paper reviewed how FEA models simulate long-term stability of cementless femoral stems and identify risk in hip arthroplasty. The geometry of implant, bone implant interface, elastic properties, load conditions all matter. Also, FEA is used in designing custom knee implants, checking maximal tensile stress, fatigue behavior, comparing with reference implants. Additive manufacturing and patient-specific designs. Custom implants and scaffolds are now being produced with AM 3D printing methods. This allows porous structures, lattice designs, patient-matched geometry. Porous tantalum scaffolds manufactured with advanced microstructural control via AM and surface modification show excellent early bone binding and clinical translation. Biomechanical principles. Considerations like load bearing, elastic modulus matching to bone, reducing stress shielding, ensuring fatigue life. Implants must distribute forces appropriately so that bone continues to remodel normally. Avoid overly stiff materials that transfer load away and cause bone resorption. Use of porous materials, gradient materials, stiffer internally, more compliant externally is one approach. Navigating the unknown, implant failure, and revision strategies. Common failure mechanisms. Aseptic loosening. Failure of bone implant fixation over time without infection. Causes include micromotion, poor osseointegration, wear particles, stress shielding. Periprosthetic fractures. Fracture occurring around the implant. Infection. Acute or late. Biofilm formation. Surface properties matter. Diagnostic tools. Imaging. SPECT, CT, PET. Newer modalities that pick up inflammation or early loosening. Computational or sensor-based detection is also emerging in research. Biomarkers, nanomaterials, or antimicrobial surface measurements, biofunctional biomaterials, help to predict or detect early failures. Revision strategies. Use of modular implants, revision stems, modular cups, etc. Bone graft substitutes, synthetic, biological, scaffold implants to fill defects. Surface treatments during revision to enhance osseointegration. where possible, designs that allow partial implant exchange rather than full replacement. The future is now. Emerging technologies and personalized medicine. Robotic-assisted surgery, precision placement, alignment, ability to reduce human error. Integration with navigation systems, patient imaging. Sensored implants/real-time monitoring. Implants equipped with sensors capable of monitoring strain, temperature, detecting early infection signals. Research into piezoresistive bone cements, electrical impedance tomography, interfacial load monitoring, e.g., using sensor-augmented materials to monitor implant cement or implant bone interface performances. Gene therapy and stem cell integration around implants. Research pushing forward integration of stem cells, growth factor delivery, gene therapy to boost bone regeneration around implants. Though still early, the idea is implants not only mechanical supports, but biologically active systems. Ethical frontiers and societal impact. Implant longevity in an aging population. As populations age, more joint replacements, hip/knee arthroplasty demand grows. Expect need for implants that last longer, promote bone health, have lower maintenance. Economics of innovation versus accessibility. Cutting-edge materials and designs often cost more. How to balance affordability with advanced performance. Consider issues in emerging markets, cost constraints, regulation, access. Patient advocacy and shared decision-making. Patients should be informed about implant materials, failure risks, revision probabilities, shared decision-making where patient values, activity level, risk tolerance, cost are integrated. In the end, mastering orthopedic implants isn't just about stronger metal, smarter sensors, or futuristic materials. It's about understanding the forces they face, how bone and body interact, and how thoughtful design can protect human lives. Keep asking why, keep pushing boundaries, because implants don't just fix bones, they must become a seamless part of healing.
If you have enjoyed the video, like it, share it, and if you are new to our channel, subscribe it. Hit the bell icon to get notifications for all our upcoming videos. Join us to excel in this orthopedic implant industry and to know more about the job and career growth which is available in this industry. Thank you. See you again next week.